Okay. I think I've got the whole board there. Okay. So, we just start with a simple example of a differential equation and what it means to solve one. So, we want to find a function y, a function of two variables x and y. It has the property that dy dx equals 2xy squared. Okay? And I said y of x and y, and really I'm kind of anticipating something else. It's just a y of x. And our condition is going to be y of 0 equals 1, right? Just some function of x that has this. Okay, very easy to solve this equation. And you've seen this. You did this in first year calculus almost certainly. Okay, but whether you did or not, it's really easy. What do? Well, we just rearrange this thing. We divide both sides by y squared. We multiply both sides by dx. You can't really multiply by dx, but we're going to pretend that we can because sort of we can. There's a meaning to it that we'll talk about later. We don't want to worry about that right now. When you solve it, the mechanics of it is if you can multiply by dx, and you get this form here. Well, then you integrate both sides of the equation. Integrate dy over y squared, you get negative 1 over y. Integrate 2x with respect to x, you get x squared plus a constant. You get a constant on this side too, but those constants get absorbed into one constant. Whatever this constant is can be added to whatever this constant is to give you another constant that's every bit as arbitrary as the other two. Okay? So we get y equals negative 1 over x squared plus c. So that y of 0 equals 1 tells us what? Y of 0, well, if x is 0, we get negative 1 over 0 squared plus c, and that's got to equal 1. The only way that happens is if c equals negative 1. That's all trivial algebra. Okay? And easy calculus. Okay? Easy integration. Okay, well, we want to look at the geometry of this situation. Geometrically, we have y versus x, and we know that when x is 0, y equals 1. Okay, so that means we have the point 0, 1 on the graph of our function. Function y of x, right? Okay? And this tells you what dy dx is. Now what's the significance of dy dx?
That's the slope.
That's the slope. Okay, so this tells me that at this point where x is 0 and y is 1, the slope is what?
0.
0. Okay, so slope is 0. So let's say dy dx equals slope equals 0 at this point 0, 1. Okay? Now we can confirm that because negative 1 over x squared plus x squared minus 1, okay? If we evaluate the slope at x equals 0, well, we take a derivative of this, we're going to get 2x over x squared plus c, quantity squared, right? And with some signs and stuff like that. We take the derivative of this, in other words. And we'll find that the derivative has a numerator of 2x. And x is 0, so the slope is 0, right? Derivative is clearly 0. Derivative is clearly 0. That checks with what we have here. Okay? Now, we can do this without knowing this. Right? And if this function is just the slightest bit nasty, we can't do the integral. Matter of fact, in many cases, in most cases, we can't solve the differential equation. Okay? But we can always do this. And there's a lot of insight to be gained here because numerical solutions of differential equations, that's usually what you end up having to do. Makes you wonder why we have to do all the other stuff, just to learn how to do numerical solutions. Well, there are reasons for that. We get insights that we wouldn't get just from a numerical solution. But in many cases, you have to do numerical solutions. That's the first thing I'm going to show you. And this also leads into why you expect to have solutions. Okay, why the differential equation, even if you can't find the exact function that solves it, does have a solution, and where it has a solution. Okay? Because many equations will only have a solution within a certain domain. Okay? And range. Okay, well, anyhow, so what do we know here? We know that this thing has zero slope here. Okay? So what we say is, well, you know, we kind of figure this slope isn't going to be zero as soon as we move away from here. Okay? And you can look at the function. As soon as we change x by a little bit, now x isn't zero anymore, so your dy dx isn't zero, right? Because y is 1. If x is a little different than 0, well, y might end up being a little different than 1. Okay? Y certainly would end up being a little different than 1. Because your slope would change. Well, your slope will change, okay. So, your slope is going to change. But if we can't integrate the function or can't otherwise solve the differential equation, we don't know exactly how the slope is going to change. So what we do is we say, okay, I'm just going to get an idea of what this thing looks like. And I'm going to follow that zero slope for a little ways. Okay, so I'm going to let the slope stay 0 all the way up to x equals 1/2. Okay? And if the slope does say 0 up to x equals 1/2, then that means I'm going to end up at the, what are the coordinates of this point?
1/2, 1.
Yeah. Slope is 0. We haven't gone up, we haven't gone down. We've just gone over to 1, right? So this gets us up to the point 1/2, 1. Well, now, what's the slope at that point? Yeah, slope is 1. That means the slope has changed a whole lot between here and here, right? Which means that most likely it changed as soon as we moved away from this 0, 1 point. And it's already 1, so chances are we really ought to be up about here rather than here, right? So we've already got an error, but we always will have an error in the approximation. Okay, just like you have errors in an approximation of an integral. Okay? So anyhow, but we're not going to worry about that. We're going to say, okay, now the slope is 1, right? That's 2 times 1/2 times 1 squared equals 1. Okay? Now we're going to follow that for another half unit. Okay? So if we follow this slope until we get out to x equals 1, what's the coordinate going to be?
Three halves.
Yeah.
1.
Why?
Or,
Because we want to make sure everybody is on this.
yeah, 1 3/2.
Yeah. You know, we're going to go, we have a slope of 1. So we come over this far, we come up this far, right? So how far did we go over? We went over half a unit. The slope is 1. So the rise has to equal the run, so we come up 1/2 unit, right? So now we're at this point, which is 1 3/2. Okay? Well, now what's the slope?
Two.
Sorry?
Two.
Now, if we plug x equal 1 and y equal 3/2 in here, you square 3/2, you're going to get something fractional, right? Of course, you're going to get to multiply that by the 2, okay? What you're going to get is 3, I think. No, I'm sorry, I used 3/2. Okay, you get 9/4, right?
If you square 3/2.
Yeah, that's the y coordinate. We square 3/2, right? We get 9/4. Multiply that by 2, we get 9/2. And multiply that by x, which is now 1. Okay? We still have 9/2, right? Or 4.5. Okay? So the slope is increasing very rapidly. Okay, so now the slope is nine halves. Now I've got my labeling all kind of messed up. I'm going to kind of put all this together and put an arrow to this point, right? All this applies to this point. And now we're going to say that at this point, dy dx is 2 times 1 times 3/2 quantity squared, which is 9/2, 4.5. Getting very steep, right? Okay, so now we go out here and we're up to the point 3/2. What? Just tell me how you're going to calculate it. You don't have to do all the arithmetic in your head.
Just plug in the y for y and x for x.
We're not plugging anything in for y at this point. What we're doing is geometrically analyzing this triangle here so we see how far we have to go up.
So the slope is 9/2, so it's going to
Slope
go
is 9/2. You're
half.
moving half a unit, right?
half that much, plus whatever it was
Yeah.
before.
So if your slope is 9/2 and you move half a unit, well then this side of the triangle is 1/2, right? The rise has to be 9/2 of that, right? I didn't say that.
1/2.
Yeah,
1/2 of
9/4. Okay?
something like that.
That's 2 1/4. But we add 9/4 to 3/2, right? We get 15/4, I think. Okay? Now you ought to be able to do the fractions. And you ought to be able to do those fractions in your head better than I can. Because I have no working memory. Okay? So I can't even guarantee I did that right.
You have 60 years more experience than we do.
Experience helps, but lack of working memory is a hindrance. Okay? I know what I'm talking about, I know what I'm doing, but watch my arithmetic, as you well know, because you've had me for a couple of other courses, okay? So verify. Don't accept my numbers. If I wanted the numbers to be right, I'd be reading off a piece of paper like everybody else my age or even 20 years less does. I don't do that because we lose the spontaneity and we lose the fun of catching me in the very rare errors that I make. Yes, yes, you're both smiling, you know. Okay, understand? Okay, well, very good. That's the idea.
So how far off are we now?
We're way off. Because you can tell we're way off. First of all, if we took the average of these two slopes, we would get a slope of 1/2, right? So we figure we're off by about that much. Okay? That means we're off by about 1/4 here. So instead of 1/2 1, it should be 1/2 like 1.25 if you want to do decimals, which you probably do. Okay? Because eventually, you know, the fractions get unmanageable and you go to decimals so you see how big these things are. Right? But I wanted to do this exactly with the fractions, just to indicate that's how you really do it until you run for your calculator or spreadsheet or computer program, right? Which is ultimately what you're going to do when you do numerical solution. But you do it by hand first so you know what's going on. Okay, well, so we're already off. And that means that the slope is already going to be off. We're going to have to square, instead of 1, well, let's see. Yeah, it's why it's being squared, working memory. Instead of squaring 1, we got to square 5/4, which gives us 29/16, which is 1.5625.
Wow.
Okay?
I'm not going to check that, but
Everybody over the age of 8 ought to know those fractional conversions up to 16ths. But since, I'm almost 10 times that, 20 times, I don't know, I can't do that arithmetic. Okay, the point is that this slope is already off by like 30%. Which means that we're going to be way short on this one, and the actual curve is going to go way higher than this. Okay? Now there's a problem with this because we have a negative here. And somehow this doesn't match this. It probably has something to do with my having done something really stupid over here. Because doesn't it all match this curve? So don't believe any of this except for the idea that you separate it, right? I mean, I can't imagine what I did wrong. And clearly derivative of 1 over y is negative 1 over y squared, right? I don't think I made a mistake on that. So we do get a negative, we get a positive here, but we get a negative on this thing, and it's a reciprocal, which means that as x increases, y ought to be decreasing, or increasing. And okay, well, there is a problem with this, okay? And actually, never mind, this is good. But this thing's got an asymptote at x equals 1, which I should have seen immediately. Okay? So what really happens is we underestimate this so much, this thing's actually asymptotic to x equals 1, and the solution doesn't go past the vertical line x equals 1. The solution's only good up to the point where this function isn't defined anymore. Okay? So we've got to be careful about the domain of our solution. I didn't mean to illustrate that. I just picked out some symbols and wrote them down and went ahead and winged it, but there's a lot to be learned here. Okay? So, okay, one. So if we make a table of y versus x, just to compare the actual solution with what we got here.
it's x squared minus 1.
Yeah. Okay. Okay, well, when x equals 0, y equals 1. When x equals 1/2, y equals what? Well, 1/2 squared is 1/4, right? So now we have 1/4 minus 1, which is negative 3/4, which is going to give us 4/3. Okay, which compares with this. We're a little low, right? Now, at 1, your solution is undefined. And you can see, if you understand rational functions at all, you got a vertical asymptote. Huh? Our solution doesn't seem to match that. Well, that's just because we've been underestimating our slopes.
So why does the differential equation only apply to the left of the asymptote?
It's basically because when you do this, you get a denominator okay? I don't want to go into that. First place, I have to think, okay? And I think I can think through that pretty quickly, but I don't want to do that on my feet, okay? I didn't stop to check the domain of this equation, okay?
Could you take the inverse?
And what it is you have a singularity when y equals 0, so, okay? When you do this. But I don't want to do that. I just want to show you how this compares to this and give you an overall warning about all the things that we're going to work out in detail, okay? Because there's a warning in this example, which I pretended to screw up so I could make this point. Okay, you know better. Okay, well, look, if I go to, let's go to decimal. Let's say I go to 0.9. Okay, what do I get at 0.9? Well, I got a square x. That's going to give me 0.81, right? So actually, I'm going to go to the square root of 0.9, just so I get convenient numbers. Square root of 0.9 is close to 0.95, okay? So I'll make a note. Square root of 9 is approximately 0.95. Just by that approximation, I've told you several times to know. Okay? And you really need to know it because you're going to need it as juniors in a tough engineering program. Okay? 0.9. Square root of 0.9 is going to give you 0.1 in this denominator, negative 0.1. Because when you square the square root of 0.9, you get 0.9. And you subtract 1, you get negative 0.1. Negative 0.1 goes into 1 10 times, and the negative of that gives you the positive 10. So we got 10. Okay? Well, we're nowhere near that on this scale. 10, that's not even 4. 10 is about there if I stand on my toes. Okay? So you can at least believe that we're going to be approaching a vertical asymptote. Okay? Here's your actual. And it doesn't go past y equals 1. By rule, it's very easy to state and understand, and we'll do later. Okay? And your approximation is here. Okay? So, lesson of this is you can get the general idea of how the thing behaves, but you miss stuff. Like we just went right across that asymptote by assuming an underestimated slope and not having a refined enough set of points here. Now for homework, I'm going to ask you to repeat this using an interval of 0.2. I was about to say 0.1, but I don't want to be that cruel at this point. It's just more calculation. 0.2, it means you're going to have like 5 steps. Okay?
And only calculate it until the asymptote?
And what?
Only calculate it until the asymptote?
Yeah, just up to 1. Because now we know that there's an asymptote at 1 if you believe this solution, which is easy to understand. Okay? So I want you to totally understand this example, and that's going to be in your homework. Fair enough?
Yes, indeed.
Well, I hate to be fair to start the course, but okay.